Okay, we are recording. We're on lecture 4, and we're going to finish up our basic sorting algorithms. Again, please remember to take your attendance survey. If you think of it, just help me keep track. Yes, question. Oh, it's at the bottom of the quizzes section. Yeah, there you go. It's kind of hidden. And thanks again for everybody for doing that. It's kind of my own quirky way of tracking this stuff. Okay, so quick announcements and we will dive in. Again, lab 3, good to get in if you can. I appreciate you guys doing this. These labs will get a little trickier as we go forward. These are kind of warm-ups, other than the lab 1, which was kind of off the charts, kind of hard, but it was a good reminder of what's to come. We have quiz 1 due on Monday. It's really just a lot of this basic stuff, some math, mostly plug and chug equation stuff. It's probably more annoying than anything. You do not really have to know all of your sorting algorithms that we've covered for that quiz. It's really just trying to cover the basics. Homework 1, of course, we're going to talk about again a little bit, just to remind you one more time. We do not have a lab today, so you don't have to worry about a lab. It's just giving you some time to work on your homework or catch up on your other labs tonight, and then everything's due on Tuesday. So we'll touch base on the homework here coming up real quick one more time. Quiz 1 prep, if you need it. This is really just covering, it really is covering lectures 1 through 3, even maybe only 1 and 2. There's some insights from the sorting algorithms there, and by way of looking at code, you'll see what I mean. But it's more logical analysis than memorization of sorting algorithms at this point. Okay, so but you might want to just burn one of your tries early so you can kind of get a sense of what's there, just in case you're worried. Now, once again, I think we'll stick with the virtual deck of cards. I do have physical cards for you. I keep forgetting to bring them down. It's so annoying, but sometimes it's nice to have this thing on the screen. Okay, so quiz is out there, and there's some code recognition, a little bit of sorting performance, but again, I don't think it's more around the performance curve reasoning stuff that we've talked about for a little while in logarithms and some stability questions, that kind of stuff. Okay. Right, and there's a Quizlet there if you want. So I think I mentioned that before. We'll keep adding to that as we go over more and more terminology. I realize it's just nice to have extra tools at your disposal. Remember that you can submit your link or your actual code. And please don't forget your Google spreadsheet, which is annoying but important for this. Fortunately, it means you need a Google email, or if you want to copy this and just give me some other kind of spreadsheet, I'm okay with that too. I just need some way to see your spreadsheet. Now, if you do share your Google spreadsheet with me, please make sure you, in fact, do give me a public link. We have about 5 folks who, it's confusing, but it takes me a while to remind them. So let me just show you what that looks like real quick so you can kind of see it live. Sorry for the glare. So when you share something over here, actually, it's not going to let me share because I'm not logged in. It's going to tell you, hey, you want to share it with anybody, who has the link. You want to, of course, say yes to that. Then just give me that link, okay? Your job, as we'll see here in the slides, is to fill in the yellow areas. So anywhere you see bright yellow, you are supposed to put something in there. So obviously you have to make a copy of this in order to change it. So everybody's going to have a copy. They're going to give me a link in addition to their code. And that way I can look at your numerical analysis that you do, okay? So you may want to run your program multiple times, but most of this is automated in main. And many of you have probably seen that. It's going to run different tests for the value of n. And when I first wrote this years ago, I made everybody kind of do that manually. So now I've got a for loop and I create a data file. So rather than writing these things down, you could just look at your data file, but you can do it either way. It's entirely up to you. So the data file that's going to get produced is produced, as I mentioned last time, in a specific format. So it's really easy to drag it into this graphing tool called CSV plot, right? So we're going to be talking about the amount of time it takes, the number of swaps, or sometimes copies. As we saw last time, things like insertion sort don't swap things. They just shift them to the right to create a gap. So we're either going to be counting swaps or we're going to be counting sorts, depending on what kind of algorithm you implement. So you got to just make sure one of these values is non-zero so that we actually have some data. If you don't do it right, I'll remind you, you can kind of come back and do that. Okay. Now, the big part of this is we're going to give you such a big value of n that you should be annoyed that you don't want to sit around and wait for your algorithm to finish because it's just very, very large for the computers that we're using. The idea is that you should use a rule of thumb to estimate based on your prior numbers, and I'll show you how we want to do that. So here's that spreadsheet again. Notice that we've got power of 2 values of n. So we start with 1, 2, 4, 8. So we're growing our number of n things by doubling it each time. That gives us a nice round way to test out whether we're getting logarithmic performance or quadratic performance. So normally the number of things we're testing doesn't grow like that. It grows kind of linearly, but here we're doubling it each time. And that just kind of gets us to this crazy number out here, 1,000,000 things much more quickly, okay? The idea is you're not supposed to try to run your program to solve the problem for 1,000,000. You can if you want, but I would like to, us all to have some intuition about this, which is really what the class is all about. So you're going to fill in these middle numbers, row 9 through row 16, and you can either drag that out of your output on your your output window for your code, which you'll see, or you can go dig in the data file. There's lots of different ways to get that stuff out of your code. And then you're going to answer this question: what is the performance of your sort algorithm that you chose or wrote in terms of its number of comparisons? Okay, so everybody should be comparing just array positions and counting those positions using the myCompare function. So that's part of your code base that I give you. So that shouldn't be too hard. Your growth of swaps will either be swaps or copies. So you can do either one, but think about what kind of algorithm you're implementing. Is it a selection sort like we'll see today, or is it an insertion sort or a bubble sort? So you get to choose, but you should describe, is that quadratic? Is that linear? What is your curve telling you? And then try to estimate what the time is for that row 20 down there, 1,000,000 things. You can let your code run for a while, but it would be nice to see if you can kind of figure that out. Okay. So that's going to be a little estimation that you can do. And I'll show you a trick here to do that in just a second. Okay. So that's the basic idea. Now, if you are running in Program is Pro, which you all can do without, needing a special account, you all give it up to 5 playgrounds. You could be doing this, or you can do this on the side. That's fine. You just can't really do it in the online compiler because the online compiler doesn't store files. So you kind of lean into this Program is Pro thing at some point here. Now is kind of the time if you want to be using it online. So you're going to get a data file from running this whole thing. And you can, if you're using Program is Pro, just download the whole playground as a zip. So it'll come down, you crack that zip open, drag the load CSV of your data file into there, and you'll get a nice graph. Okay. Now, if you're doing this in VS Code, same thing. Just load that CSV file from your code area up into this. And now we get to see your compares or counts, or sorry, compares or copies, and your swaps, right? And you can turn on the other curves, as I mentioned before, to kind of see if they hockey stick up kind of like a quadratic, or do they come closer to a linearithmic. So just by visually comparing them, they should be, somewhat identifiable, especially if you're implementing a canonical implementation. You're going to get a perfect quadratic curve or a perfect linearithmic curve. Okay? And you'll also see time there. That's the really interesting one because it's like, huh, well, everybody has a different computer. Even when you're running in the cloud on program is, you're gonna maybe get a different computer, or maybe you have some contention that slows that down. So it's kind of interesting to see, does time grow quadratically, or is time like a little fluid, in terms out in the real world? So there's some interesting observations there. So all we're really looking for you to do is kind of assess the data. This is just one way to do that. And then come back and fill out that spreadsheet. Okay, so all this graphing stuff, you could just say, I'm going to skip that. I think I know what's going on here. And I'm not going to count any points off. So you can kind of let go of all that extra stuff if you really want to. But it is kind of nice to be able to see the graph and go, oh, that's really what I'm doing there. I see as the number gets bigger and bigger. Okay. Questions on that part so far? Okay, cool. So hopefully that doesn't take a ton of time for everybody. It's just kind of getting you grounded in this performance language that we're going to use the rest of the semester. So we're going to pick up the selection sort today, which was the one that came after insertion sort. We didn't really kind of get to look at that last time. And it's going to be our first swapping sort. I'd say swapping at a distance. Bubble sort swapped with its neighbor if things were out of order. This one is just going to be kind of a crazy swapping strategy. And this will be our first unstable sort for that particular reason. We'll show you that. Then we're going to look at this crazy one called shell sort that hardly gets used anymore, but it's an interesting historical item to study. So we'll kind of fly over that one kind of quickly. Then we'll talk about shuffle sort, which is really useful. It's like, how do I randomize something in linear time, which is a really good thing. Anytime you get linear performance, that's a pretty good thing. Counting sort, that is brilliant. So I call this the rate my professor problem. This is really a linear sort. So it's like, how could I sort things in linear time? Like there actually is a way to do that if you have lots of duplicates. Like if you wanted to sort all of the products on Amazon store in terms of their 5-star rating, you only have 5 ratings. So that's a much different problem than sorting a million different possible values. So this particular sort is really unique and good for things where we have lots of duplicate values that we're trying to put in order. Okay, so we'll actually kind of dig into that at the end if we have enough time. So this is where we've been. This is where we're going. Next week, we'll pick up the merge sort and the quick sort, and we'll eventually pick up the heap sort a little bit later. But that will take us through the end of all of this sorting muck. And then we'll move on to the more fun data structure stuff. Okay. So that's kind of a quick view of where things are. So Quizlets, I know I mentioned these. We'll see the arithmetic series kind of more or less in code a few times, and then we'll just start waving our hands at it in the future. Just remember that arithmetic series types of algorithms are essentially quadratic. They're not n squared, they're kind of n times n minus 1, which really is still quadratic. It's just a little bit better than quadratic. Okay. So we would say if something kind of implements an arithmetic series with an inner loop that gets smaller and smaller and smaller, or bigger and bigger and bigger, by a difference of 1, that's going to be sort of quadratic. Okay. So here's just one way of looking at that. Here's a loop that is quadratic, n times n, right? The inner loop doesn't shrink. Okay. Here, the inner loop is shrinking in this formation of the inner loop because y starts at x and x is growing. So the inner loop does fewer and fewer iterations every time. And that's going to essentially give us a consistent change from loop to loop to loop. And that's going to be our arithmetic series, right? So essentially it's n times n plus 1 over 2. So it's better, but not really any different than quadratic at a really high level. Just a different formulation over here, right? We're still reducing the end goal of the inner loop by 1 every time. We just sort of shuffled the logic around. We're still getting a quadratic arithmetic series kind of thing, okay? So good to recognize that stuff, not stuff we're going to, dig into super deep very much in the course, okay? So remember stability. We talked about if you reorder two things that are already in order, you have broken the stability. So if we ever investigate a sorting algorithm that does swapping at a distance, which we will do today, you very much are looking at an unstable sort. Okay, we'll see that a few more times in the course next week when we look at more recursive algorithms. So why would we ever want to do that? Well, maybe we only ever want to sort by one thing, the number. But if we want to sort by first name and then last name and then middle initial, we're going to need a stable sort. So you get to pick your poison depending on what you're trying to accomplish. So that's stability. And that is an important concept to know about sorting. Is it stable or is it not? Okay. So just so you can see at a glance, bubble sort is, insertion sort is. Today we'll see selection sort is not, shell sort is not, shuffle sort of course is not, because it's just randomization. And then these we'll see next week. Okay. So high level, we'll kind of come back and review that and remind you that. Remember that we can say that as n grows bigger, things never get slower. That sounds almost magical. Or we can say as n grows bigger, the performance of something, copies, swaps, time, grows proportional to n. 2n, 3n, n over 2. So there's a constant out here we often wave our hands at and say, well, n is really the dominant term. The factor there, or the coefficient, doesn't really change the fact that it's linear. It's just a higher slope. And we'll see some of that in the graphs here that we're looking at, okay? Logarithmic, we'll get to logarithmic here next week. We'll get to linearismic next week. Quadratic, we're seeing a lot this week and a little bit next week. Cubic, we're just going to try to avoid like the plague because that no one wants to do anything with that, okay? And I won't take you through all the curves again, but you may find those useful when you're trying to analyze your homework analysis if you feel you need some extra help, right? Remember that insertion sort progressively builds up the sorted side by figuring out where the 1 goes and shifting things to the right as necessary. So insertion sort shifts, it doesn't swap, okay? And our sorted side grows by 1, and of course the unsorted side shrinks, okay? So that's the hallmark of an insertion sort, that shifting to the right thing, okay? So shifting is cheaper than swapping. Swapping requires 3 copies. Hopefully we all kind of get that. In order to swap 2 things in an array, I got to copy something to a temp, copy something into the open position, then copy back from temp. That's expensive. Shifting is just 1 copy. We kind of move something in a temp. Okay, that's a copy, but then we shift to the right a whole bunch of times. So that can be cheaper than swapping. Okay, so depends on how it all gets implemented, but keep in mind that those 2 things have different cost profiles. Okay. And let's see, selection sort algorithm. Oh yeah, we haven't done that yet, so I'm going to review or skip over this because we're going to talk about this today. We haven't really talked about selection sort yet. That's coming up, okay? Small point on lab 2, not a big one, but notice that if you don't add 1 to your new guess or your new boundary for low, you're just reducing the efficiency of your divide and conquer search. So if guess is not the secret value, then don't include guess in your new range. Move beyond it by 1 in the case of our lab 2, okay? Similarly, if the secret value is lower than guess, then move to the left of the guess, because why waste time checking the guess again on the next divide and conquer cycle? Okay, so these little teeny tiny -1 +1 things will blow us up when we start doing recursion next week. So we gotta be really precise about our new ranges. And so in this case, it's good to just eliminate that new guess if we know it's not really the answer, okay? So low, high, where is the new guess? It's too low, okay? Secret's up there. So move the low past the new guess by 1. So we're not wasting time searching that again. Okay, so for some of you who felt like, my performance seems a little bit maybe less than what I thought it would be, maybe that's why. Maybe you would have got a little more efficiency out of it by moving beyond that midpoint. Okay. So sometimes those small things really matter. Okay. And then we pick a new midpoint and on we go. Okay, let's talk about selection sort. Selection sort is pretty similar to insertion sort. We have this idea of an unsorted region and a sorted region. So if we start out with everything unsorted, we pick the smallest thing that we can find and we swap it what's at the leftmost region of the unsorted area. So the 3 is the leftmost region. So let's find the smallest thing and then let's swap these two, okay? Swap them, okay? So now we know that the 1 is in the right place and we just sort of ignore the 3. It's like, well, yeah, we know it's going to be kind of coming back our way, but we're just going to push it out of the way for now. And then we update our ranges. So now we have, that's the unsorted and that's the sorted. So search for the smallest in the unsorted area. Once you find it, swap it with the leftmost side of the unsorted area. And off we go. Now, as you might expect, we're going to have to do multiple passes, just like bubble sort and insertion sort. But also, we're probably going to break stability because if there were 2 3s in there, we're probably going to end up crisscrossing and swapping them over the top of each other unintentionally. And that is very likely going to break stability. So in other words, if that was students' names in class at college at Marin and we were sorting by their last name, then the first name, we would probably not get a very good sort in the end if we used a selection sort algorithm because it is inherently unstable. Okay. But that's the key idea behind selection sort. So here's kind of how that looks, and I won't run this whole thing out, but we sort of look at the whole thing as unsorted. We sort of consider that 3 is the leftmost item, and then we go looking for something smaller than that, right? And if we find it, and you can kind of see ahead, we're going to remember it. We're not going to swap right away. We're just going to remember it. And that's now our smallest thing. And when we get to the end, then we swap and then reduce the range, okay? Now we start again. 44 is the smallest. 38 is the smallest. 05 is the smallest, right? So we're just remembering the position of the smallest thing. And then we'll swap it with the 44 at the far left. Okay, so I won't run you through that whole thing, but it's just another kind of nice way to visualize what's going on there. Okay, so eventually we get there. Okay, so not too much different code to worry about. So if you want to see it this way, right? So there's us looking for the smallest thing, right? We found it. We're going to swap, and now the 4 or the 7 and the 9 are swapped, etc. Okay, so we'll look at the code here in a second. I used to not have the video, so this was all I had. So probably this is a little bit redundant. But you can see that we kind of got to go over the whole thing to find the smallest thing. And even if we don't swap, we can't quit. There's no early exit like we used to have with bubble sort. We still got to kind of keep going and checking through everything. Okay. Now, if we wanted to sort descending, we just switched the algorithm for comparison around, right? And if you recall at the end of the last lecture, we said, oh, don't rewrite the code, just rewrite that one little piece where we do the comparison. Like, is it greater than? Okay, swap. Now we just check, is it less than? And we swap. Okay, so things are relatively easy in terms of altering our sort order. Okay. So when you use a library function that does sorting and you indicate somehow through some Boolean or whatever that, hey, I want to invert the sort, that's all it's really doing. It's just flipping the sign on the comparison. It's not really executing much really different code in the end there. So let's just try this real quick with our digital cards so we don't forget it too quickly. So let me bring up our cards. I'm going to put out 8 cards, treat them as unsorted, and just do a quick insertion sort. Sometimes these things are helpful to, anchor this stuff. So I'll shuffle. Okay, 8 cards out. 1, 2, 3. You can try 4 if you want. I'll try 6. Save ourselves some time. Okay. So here's our cards. So they're all unsorted. So I got to find the smallest one and swap with the leftmost. So I can kind of see that the smallest one here is 5, but I got to keep going until I get out to the end to see if there's anything smaller. So it really doesn't matter whether you choose this one or this one. So I'll just sort of do the swap, right? And now this is sorted. Okay, repeat process. Where's the smallest one? Okay, I'm going to swap it with the 8. Okay, now that's sorted. Okay, where's the smallest one? Swap with the king. Okay, that's sorted. Move that over. And you can kind of see where we're going to go with that. Okay, just that simple. Okay, relatively speaking. Okay, but if there was an extra 3 in there, let's see if I can get lucky and get a duplicate in here. There we go. So if I had this thing out of order, and I just to illustrate that this can happen, of course, right? So I'll put the 8 over here, right? So the 8 of diamonds should never change places with the 8 of clubs, okay? That's the hallmark of a stable sort. But let's see what happens. So, okay, who's the smallest? Okay, 5 is the smallest. So we'll swap these two. Okay. Now who's the smallest? 5's the smallest. Okay, we'll swap these two. Now who's the smallest? 8's the smallest. Now this is an interesting choice. Would we swap these? Well, they're equal, so we probably should just leave them where they are, right? So we might get lucky this case and not break stability, but you can see how it can happen that this sort would actually break stability, right? So otherwise we'll swap this, right? Then we come in here and we swap this one, whoop, swap this one, right? And we get lucky this time, but it is not guaranteed that we would not end up swapping the 8s. It can actually happen pretty easily. So I think I just got lucky there in that case, okay? But that is our selection sort. Now let's take a look at the pseudocode real quick. So there's our outer loop. Okay, we go while I is less than the second to the last position. Okay, that's because we're going to swap with I and I. We're going to, well, we potentially will go one further to the right. Okay, so we'll remember what we think the minimum value is to start, which is in the 0th position, and then we'll go searching for something smaller. Okay. If I find something smaller, I'm going to update M and keep looking. So the middle part is really just looking for the smallest thing. And when we fall out of that for loop, we are ready to do our swap. And then we wrap around and reduce the range of our unsorted area and repeat the process. And that's our selection sort. It's really not too bad. A little annoying to try to understand the code without comments, but some of us can read code like that without comments. I like putting comments on code like that because it hurts my brain every time to relearn what's going on there. So it's nice to have even just those comments there. Okay. So we have this to n, and then we reduce the range by 1 every time. That's our hallmark for an arithmetic kind of performance, which is really just quadratic. Okay. So you could look at this or any algorithm that was this straightforward and say, oh, that's quadratic in regards to comparisons. Okay. Swaps may be something different, right? That's not on the inside of that inner loop, right? So the number of swaps we have there might have a different performance than quadratic. It's not a given that they're both quadratic, okay? So heads up on that for your homework, because sometimes people will be like, quadratic, QED, like everything's quadratic. It's like, nope, one of them's quadratic and maybe one of them's linear, okay? So heads up for that. So that's our selection sort. And if we were going to change it the other way around, just change that -1 to a +1. We're just changing what we're comparing there. It's a really elegant way to do that, okay? Without rewriting a lot of code and logic. So as it turns out, our best case scenario is n times n minus 1 over 2, which is not great. If things were already in order, this sort is going to actually cost you quadratic time just to find out that you don't need to do any work. That's pretty bad. So the selection sort is not a great solution for really large arrays, and in particular where maybe they're mostly sorted. So let's say it's Facebook and they resort every user, a billion users a day, but every once in a while we get new users at the end. We got to sort them in. Well, the data is mostly sorted, so why pay a really high cost to go, insert just a couple things? I mean, I'm oversimplifying, but so anyway, that's our comparisons, and our swaps are linear as we kind of anticipated, okay? But notice that the worst case scenario where I have a descending list where I want to sort it ascending is actually faster to do with selection sort than a random. The reason, of course, is as you might imagine, when I swap the one with the 6, I'm fixing two things at once. And then I'm fixing another two things at once. It's just lucky that we kind of would have that situation. So we end up doing far fewer swaps. Okay. It's not really going to happen in real life that way. So it doesn't really bias a lot in real world situations. This is probably more likely what we end up dealing with. Okay. So swaps are linear as n grows, comparisons are quadratic. And probably if you looked at the time, you would probably see your time is quadratic because that's the dominant cost of both of those things combined. Okay. So it might not be exactly quadratic time growth, but it's going to be pretty close. So that's the insight on how we're actually assessing these things. And you'll see these things probably in your homework in subtle ways. Okay. Just remember this one is unfortunately not stable. Questions on that one? Okay, very good. So I'll leave this to you guys, but it's good to look at the code from time to time. But if you want to dig in, just try to figure out how to cause this thing to sort itself in descending order. Okay, it's good logic check to make sure the code, your brain is reading the code properly. Right, and really, again, it's just a matter of changing the sign of that comparison. Okay. If this is 1, that means this is bigger than this. If this is -1, that means this is less than this. If they were equal, then you get a 0. Okay. Okay, so let's look at shell sort. So this is a crazy sort, which is named after one of the early computer scientists in the 50s. His last name was Shell. I can't remember his first name. But this has fallen out of usage in modern architectures because modern architectures, for those of you who like hardware, use caches. So you kind of don't like reaching out to go get memory. It's like going to your storage locker, 2 cities away to go get a pair of socks, right? So modern architectures like to collect as much memory locally. Those are typically known as the L1 and L2 cache on Intel architecture. Hold that information in memory until something pushes it out. So we call that locality. That's like, hey, go get me what's kind of probably the stuff I'll use and keep it around on like a desk, and then I'll put it away later. Shell sort is not very friendly with that kind of modern architecture, and we'll see why here in just a second. So it really is a historical kind of curiosity, but it is the way people think when they design algorithms. They were like, hey, insertion sort works really well with short lists. That's its sweet spot. So what if we decided to break down a really big problem into interleaved sections? So if you kind of take your fingers and kind of from two hands and you interleave them, that's what we mean. It's like, what if I had a lot of things, 10 things, like 10 fingers, but I just decided to sort the left hand and then sort the right hand with an insertion sort and then step back and sort the whole thing. That's the big idea behind shell sort. It's like, let's pick some like interleaving numbers and then do little sorts and then back up and make the sort a little bigger and a little bigger and a little bigger. So we're solving smaller problems, but eventually we're moving toward order. So crazy as that idea sounds, it actually was for a time very good state of the art sort. So here's an example of insertion sort where we're working in a particular gap size, 1, 2, 3, 4. So the yellow numbers are all part of the same slice, if you will, or interleaved, okay? Sorry, gap sort of 4. So 1, 2, 3, 4. So there's 4 between every yellow one. So we do an insertion sort on that, and then we slide over and we do the green ones. So we're still sorting on a gap of 4. We slide over, do the purple ones, and now we've done everything we can do at gap 4. So we drop the gap down and we do it again. So we're slowly stumbling toward order. And the idea is that insertion sort is so good with these shorter lists that we'll maybe actually come out ahead in the end, okay? So the gap numbers that we choose are kind of part of the magic. It's like, okay, well, what are the gaps? What should we use? Should we go 4, 3, 2, 1, or 10, 9, 8, 7, 6? How do we know? Okay. So that's the idea, though. And as it turns out, if we look at insertion sort, just to kind of looking back, our best case scenario, of course, is linear, and the rest of the stuff is quadratic. But if things are mostly sorted already because we were stumbling toward order, maybe we get a pass, right? We get done really efficiently, and we can go on to our next gap. So that's why they chose the insertion sort. Okay. So here's the gap sort on 4s again, right? So that gives me that. So the yellow ones are sorted. Now we're going to sort the green ones, right? So we get that. So now instead of 9, 7, 10, 11, or 7, we got, that. So that's what we mean by progressively sorting at gap 4. But we still got to then go to the next smaller gap size. So we're not even really done yet at that point. But we're definitely in a better place, okay? So whatever gaps we choose ahead of time, that's where we go next. Maybe it's a 3, okay? So typically what we would do is go 4, 3. There's no point in doing 2 because that is a factor of 4. And we will see very soon that when we get to hashing and heap sort, that, or hashing rather, that prime numbers are kind of really cool when it comes to doing things like this. So in this particular case, 3 is a really great number. It's not a factor of 4. So it really means we're working in a new way on the data with this idea of doing an insertion sort. So we don't want to have a gap size, any bigger than half of n, as it works out. So, sitting down, looking at n, picking your gap sizes, and then sorting is the process we have to follow for any kind of a shell sort application. Okay. So each of these sublists gets better and better. And finally, we're just doing a normal insertion sort. At gap 1, we're doing an insertion sort, but it's already almost completely sorted. So the cost of shifting things to the right is not as big. And somehow magically, we in theory come out on top. Okay. So, but the story is always a little more complex than it sounds, right? From the marketing speak. So let's take a look at some of the insights. Okay, well, here's more of the gap sorting. So sorry to kind of take you through all this, but if you want to come back and kind of convince yourself of what this means, this is gap sorting on 3s. So the yellow ones are sorted, the green ones are sorted, the purple are sorted, but overall, still not quite there, okay? So then we go to the 1, and now you can see we're kind of sort of heading toward sorted. It's not totally sorted, but the work left to do is really small. So insertion sort gets that thing done pretty efficiently just by shifting a few things around, okay? Kind of crazy that people, come up with this stuff, but indeed, that does get us our sorted solution. Now, choosing gaps is a huge area, or was a huge area of research. And in fact, it's one of the examples of an area of algorithms that no one has ever actually closed the book on. So there are still people probably, people who are more out of the mainstream now, but who are, studying, hey, what kind of gaps should we use? Okay. And what's the largest gap we should start with? That kind of thing. It's an open problem. No one's really ever definitively proven that we know the final answer on that. But probably no one's really doing a lot of heavy research on that. A couple algorithms have been suggested. So if we start with some value of k and say 3 to the k minus 1 over 2, and then drop the value of k each time, we get a new gap size, like 364, 121. And this gives us some numbers that, generally speaking, don't overlap with each other in terms of their factors. And it results in a very good kind of shell sort. Other algorithms say 2 to the k minus 1 for choosing our gaps. Okay. It's kind of crazy, but there's a lot of math and theory behind deciding on these quadratic equations for choosing gaps. Lots of ways to actually do that. So, and then we work down until we get to 1. That's the whole idea. Start at the biggest gap, slowly bring ourselves down to 1, which is essentially our insertion sort. So Sedgwick, who is kind of one of the authors of the book we follow for this course, is one of the authors of many of the original art algorithms back in the day. And he, just to let you know, like, he spent over a year looking at, different kinds of gap strategies for this. Okay. So here's a slight visualization of what we see, a random input, gap 40 sorted, right? So you can kind of see we go across and just interleave and sort the interleaves. Then we change the gap to 13, right? Slowly we're getting more, it's looking more sorted. And then we finally get to where we want to be on gap 1. Okay. Now I won't take you through this stuff because, again, this is kind of historical, but it is an interesting and good example of, how exotic some of these algorithms can be. So if you want to work through these and try to figure out what they are, just sort of think, okay, how do I fill in the blues in a sorted order? 1, 8, and 4. Okay. 9, 2, and 5. Right. And then eventually you'll get to a perfectly sorted list at the bottom. Okay. Looking something like that. And those are on gaps 3, 5, 3, and 1. Okay. So here's another one, right? The blue ones, then the orange ones, then the green ones, and then move down a row, etc. And we should get to our sorted list. So how ugly is this code, right? So we're going to skip over this for a time because doing this with cards is kind of a little tough to do, but you would do your 8 cards on your desk and then treat the first card as sorted and kind of just remember, your gaps and sort in this interleaved section, okay? And you're going to, of course, need multiple passes to do that, okay? And see if you need the same number of passes every time you go over the top of that. So whenever we write an algorithm or analyze an algorithm, we want to think best case, worst case, average case. So it's always good to bracket an algorithm with those kind of questions. Probably most people are worried about the worst case scenario. If you can minimize your worst day ever, life is actually not too bad, okay? So sometimes people do crazy things, like if your worst day ever kind of is limited by randomizing the sort, like literally sorting it before you, or shuffling it before you sort it. Hey, let's do that. And we'll see some algorithms that actually need that. Okay. So let's see if we can take a look at the analysis for this stuff. First let's look at the pseudocode. So for each gap size, I've kind of waved my hands at that, but let's say we've got an array with some numbers that are pre-selected somehow. I'm going to just use that G gap size inside of what is essentially an insertion sort. I've kind of woven the G into the classic insertion sort code so that we're kind of doing an insertion sort, but by hopping over those interleaved sections, whatever the particular current gap size is. And normally we'll be told the gap size when we start out our sort. Someone will say, okay, we're going to use these gap sizes for that value of n. but maybe we have to calculate it, but we're leaving that out of the pseudocode here. If you want to take a look at this performance, you're more than welcome to do it in our kind of implementation there on program is. But when you see this idea of incorporating a shifting G or gap size, you kind of know you're dealing with the shell sort there. So if you think about it, this kind of interleaving thing is why it breaks the L2 cache on modern hardware. You're reaching very far to do this sort over a really wide section, and it's having to pull in this pile of array, and they call that cache thrashing. It's like, hey, go get me that thing from storage, and then I'll tell you to go get another thing from storage. It's really not a very efficient way to actually do things. So there's our insertion sort. There's our shell sort. It's really just the insertion sort algorithm slightly moved around a little bit, incorporating the G. Okay. So the outer third loop here is really just next gap size, next gap size, next gap size. And as it turns out, it can be more optimal, but if we kind of do it in real life, so this is me running the algorithm, the code you just saw for 512, and I always print out what are these equations for that n so we can compare. It's like, hey, well, what is that? Where does that fall in the list of these things? And that's what I hope you'll kind of be able to do with your homework. So it's like, let's see, number of compares was 15,000. That's kind of fallen in the range of, that n times n minus 1 over there. So probably it's quadratic, but let's check it, see what happens if we double n. So if we double n, we're falling still in the range of quadratic, n times n minus 1. It's an arithmetic kind of equation. And same thing over here. So really, the performance of the algorithm is not surprisingly close to those average numbers. Yes? Say again? Oh, I'm off by. Oh, I got that wrong. Did I actually point to the wrong one? Yeah. Oh, it is, isn't it? Wait, 1, 2. Yeah. So in that case, we would say it is proportional to. So maybe there was something in my algorithm or my counting that had me off by a constant factor. So the question would be, why is that? So maybe I have an instrumentation problem in my data. Yeah, thank you for pointing that out. The number of copies is also off by about a factor of 10, but it drops us in that neighborhood more or less. Okay. But that's a good one to note. I'm going to write myself a note and come back and see where did I, unless I transcripted that data wrong in some sense. But it lines up with the expected performance on averages that these things tend to be quadratic, even though some days with certain data sets, we might do better than that. But sort of reflecting on what we're trying to do with our homework, if I was to lay all this data out, what we'd like to be able to do is sort of not only look at that curve data, but you can cheat and say, hey, what is the proportional change from here to here? So it turns out that this number divided by this number tells me that it's grown by a factor of 4. So if I am doubling n and my cost goes up by 4, that's a pretty classic quadratic growth. And you can play this trick with your homework. If you see that n doubles and you get a quadrupling of your swaps or copies or compares, then you're looking at a quadratic change, right? You're even if it's scaled by some value, it's sort of quadratic. Now over here, maybe we're not seeing that with our comparisons, right? So you'd have to do that comparison, divide one by the other and see what you get. But over here, if we haven't, copied in the seconds, we could still use, this factor to project outward what our time is. If I happen to know the number of seconds here and here and here, and it looks like they're quadratic, then just carry that forward in time and see if your estimation matches what your actual results are. Okay. So we wouldn't really care about this on a regular day, but this is our foundation for the class. So we'll really study it up close for homework 1, and then we'll move away to the theory and away from all this empirical stuff. Okay. So generally we're in the quadratic space, which is just not great. Next week, we'll be looking at n log n or linearismic, which is much, much, much better than this quadratic stuff. Okay. But there's a way of estimating swaps or copies just by multiplying by 4 each progression, assuming it's quadratic. And you'll probably find that that estimate is pretty close to what you're going to see. Okay. So that's just one way of doing it. If you find another way, that's great. So our best case in some scenarios for some gap selections can get us close to n log n. That's what we call linearismic, and we'll get more familiar with that next week. But probably your worst case or average case, worst case is going to be around n squared. Average case is unproven. There's lots of different kinds of research and theories on what would be the average. And it really depends on your gap selection, which people are still studying, and it's not stable. And we have the, cache thrashing. So we tend to not really use this thing so much anymore. Okay. But that's our shell sort. And, we study it because it kind of shows us the evolution of sorting, but probably don't see it used so much. So we're going to leave that one behind unless anybody has any other questions. Okay, quick one, shuffle sort. It's kind of a misnomer. This is like really cheap randomization. So a naive way to randomize things, and I have done this before in my life where I'm like, oh, I'm really clever. I got some numbers and I want to randomize them. And so I'm going to assign a random number to each of these numbers that I want to shuffle. You can see my numbers are in order. So I want to shuffle them. So I assign a random number and then I use the random number to sort them. Okay. So I apply my best known sorting algorithm and I feel good about it. I think, I've done the best job I possibly can. And I get things in random order. Okay. So that's not the wrong answer, but its performance is limited by the fastest sorting algorithm we can come up with. Okay. So that is really going to be n log n, which we, again, will look at next week. But that's not as good as we can do, right? N log n is great for sorting, but this is kind of a special case situation. So Knuth, one of the early researchers in this, just came up with a very simple approach. As we move from left to right, pick something at random from the left and swap with it, okay? So that means we're never going to take more than n-1 swaps to randomize the whole thing, which seems pretty obvious in hindsight. But, a lot of people were doing it wrong, I guess, back in the early days. So we just need a good random number generator, and we can have linear time to actually generate a shuffle or a shuffling of the deck. So like if we say 2, we're looking at 2, obviously there's only one position, it's position 1, so we swap with that. 3, we got a 50-50 chance. What am I going to swap with? Swap with the 1. 4, pick one and swap, and on we go. So we're really only doing the n-1 swaps, okay? And we're done. We just have to have a really good random number generator so we are sure we're picking things from random at the left. Okay. So that's known as a shuffle sort or the Knuth sort, since that gentleman kind of invented it. And it's linear. n-1 is considered linear. It's proportional to n. Okay, so it's close enough. Okay. So once again, I'll let you guys kind of do this on your own. As long as you understand the concept, you're probably in good shape, but doing it physically or digitally can actually kind of help you remember this stuff beyond the end of this class, okay? But probably when you call a C++ shuffle function from the algorithms library, that's probably what it's doing, a linear sort, linear time performance sort, or shuffle rather, not a sort, shuffle, okay? So there's the code for that, right? So there's the array, if n is equal to 1, return. pick a random position to the left, right? And then if they're equal, continue, otherwise swap, something like that. Fundamentally linear. One for loop, right? Notice there's only one for loop there. That's another clue that you're probably dealing with a linear situation unless recursion is involved, right? So we haven't done any recursion here yet. So that would give us something fundamentally different. Okay. Questions on that one? Okay. And I probably said before, this is kind of like memorizing a bunch of card tricks. It kind of really is. Like, there's not a lot of similarity between shuffle sort and shell sort, for example. So no one expects you from this class to go memorize all this stuff. The key understanding is the strategy and the language we're using to achieve these things. Okay. So now, is there a difference between the best and the worst cases on this? So we are going to slowly start talking more about this phrase called tightly bound. So if the performance on the best day and the worst day based on the data, right? So was the data in order or was it random? Doesn't matter, right? The best case and the worst case are going to be linear, right? That is what we call tightly bound. That algorithm has tightly bound performance. It's not going to wobble a lot depending on the data you apply it to. So that's another key term we want to keep in mind for performance. The lower and upper bound are close to each other, more or less, then we know that's a tightly bound algorithm. Okay. Okay, and we'll run into that more. Now, here's our last sort for the day, and then we'll get you guys out of here a little on the early side for once, for those of you who are not going to be staying for lab. Counting sort. So not going to be on quiz one, but we're going to have this on the midterm, the final exam, as far as your understanding of it goes. So when I talk about understanding, I mean, if I say, hey, I got this problem for you, you got to sort all the products on Amazon that have ratings between 1 and 5, and there's a billion of them. I want you to be able to go, aha, there's only 5 kinds of things. That's a counting sort. That's the kind of interview question or the insights that people want you to have coming out of a class like this. They don't necessarily want you to just memorize counting sort. They want you to choose the right tool for the problem they're presenting you with. And they're going to try to disguise the problem in different ways. So that's just testing our ability to think openly about these. That's the kind of understanding we want to get from this course. So let's look at this counting sort or histogram sorting. So where you have a lot of duplicates, like, Rate My Professor or something on Amazon.com, we have a number of things, and then we'll call it R, the number of unique items. So if it was Amazon, it's 5, like 5 stars, 1, 2, 3, 4, 5, or maybe 6, because if you get 0 stars, okay? So that's R, okay? And so here's our array, and for the moment, I'm going to use letters instead of numbers, and I'll show you why. So remember that for most of you, I hope you know this, that letters are characters and they have ASCII IDs. So in C++ in particular, it's really easy to convert a character into its ASCII ID and use that as a place to store the character in an array, okay? So we can kind of think, for the moment, we're going to pretend that A goes in the 0 position and B goes in the 1 position and C goes in the 2 position. It's not really true, but if we use their ASCII IDs and we imagine a big array of every possible character in the ASCII set, that's really only 127 characters for a normal ASCII set. So it's not a very big array. So we have an array for our data, and then we have our counting array, which is going to hold how many of each letter. So what are the frequency of the A's? So you can see I have 3 A's there, 5 B's, 4 C's, 3 D's, and 1 F. So I need to build that frequency array by analyzing the data. And then we will use that frequency array to sort the data very quickly. Okay. So let's look at this algorithm in detail. Okay. So if we have 16 professor grades, it should make sense that 3 plus 5 plus 4 plus 3 plus 1 is going to be 16, right? That's the key to doing our sort, is first building that frequency array and then using it to redistribute each of these things in reverse order. We'll deal with this one, then this one, then this one, and figure out where to put them in this particular array. And it is surprisingly elegant. You might look at it and go, I could do that, but you'd be surprised at how often you get that stuff wrong. The cost of this algorithm, as it turns out, the trade-off is memory, because in order to sort, we're not swapping anything, we're not copying to temporary, we're moving it from ARR into AUX. So we gain some speed, a lot of speed actually, but it costs us 2n. And by that I mean the array is of size n, and I need another n for this algorithm to work, plus an r. That's the counting array. So that's not bad for memory that's really cheap. I can have 2n pretty easily. It seems like it's expensive, but a million things. Okay, I need an extra million in memory, but I can go really fast. Okay, so let's take a look at how that works. Okay, so what we're going to do is essentially map these things in a very clever way by working backwards. Okay, so, and notice that the position for the last A is 3, the position for the last B is 3 plus 5, obviously, right? It's sort of an offset from the end of the A's. That's where the B's go. So if I wanted to know where the end of the B's are going to go, it's always going to be the number for the B's plus the number for the A's, okay? So keep that in mind as we kind of go forward here, okay? Not a lot of code, really kind of clever. So if you wanted to do this, again, for the sake of time, I'm going to leave it to you. But the subtlety of this algorithm can be found in doing this with the cards, because if you don't deal them from the bottom up, you will break stability, okay? So if you follow these instructions to the letter and you work from the bottom up of the pile you created here, then you will preserve stability. If you don't, then you've broken stability. And you don't need to break stability with this particular sort, which is pretty darn cool, okay? So let's take a look at the code, okay? But it turns out that if everything's already sorted, right, we only need 2 passes. And if everything's descending, then that's going to be our worst case, but we will still actually end up executing it in pretty good time, okay? So let's look at the pseudocode for this, which I think is just really cool. And then we'll do a little animation that hopefully brings it home. So somebody gives us an array. They give us our auxiliary array. I should have called it aux. How many things and how many unique values? So I'm going to need to dynamically, or not dynamically, but inside of my sorting algorithm, create my frequency array, okay? And my first pass is going to be building the frequency array. So this is already maybe a little tricky for some of us. So I'm saying, okay, for each value I in array, go to that particular position of the count array. So you might be like, hold the phone. So I'm starting in position 0, going to position C in the count array. What does that mean to go to position C? Well, if we convert that to its ASCII ID, and for the moment, let's assume that the ASCII ID for C is 2, like 0, 1, 2, A, B, C. So we're going to simplify for the moment. So we're basically saying, hey, go increase the count for position 2 of the frequency array because I just found a C. And then when I find a D, I jump to the position in here for the D and I increment that one, okay? And we're assuming, maybe unsafely, that they're all 0 to start, but we are dealing with pseudocode here. So we're slowly accumulating, jumping around all over that count array based on what letter we're seeing and slowly building up those things. And we're using the ASCII trick of converting an ASCII character into a number position, right? So we can use that to look something up in there, okay? So that's tricky bit number 1. And of course, this means increment that, what's at that location in count. Once I have those frequencies, I'm going to build up an offset by adding the previous frequency to it. So if this was a 3, 5 plus 3 is 8, 4 plus 8 is 12, 3 plus 12 is 15, etc. So you're probably like, where are we going with this? Okay. So now I have everything I need to do the sort in linear time. So I work backwards from this position and I say, hey, where's the last F go in my output array? Okay, well, I'm going to go to the count array, find where the last position is for the A's, okay, subtract 1, and that's where I'm going to put that thing, okay? So array of I is an A. What's the count for the A? Subtract 1 from that. That's where we're going to put that A. Seems kind of crazy. We're filling in the A's in reverse order, and I'll show you an animation. And we decrement the count because we just took care of one of the A's, okay? So that is a pretty cool piece of code, I have to say. I kind of, thought, easy. But then when I really looked at it, I'm like, this has got some really clever stuff in here. Okay. So we initialize, we count. Why did I say C out? That's an N in there, little typo. And then we distribute. We actually do the sorting part, counting it, copying it back into the output array. So that's N plus R. So that's 2N plus R. That's linear. Linear with regards to N and R. So if R is small, doesn't really add that much to the cost. And that's a very fast sort. That's a linear time sort, and there aren't too many linear time sorts like that out there. Okay. So let me show you a little animation, and we'll get you out the door here before too long. So here's our data. Okay. And here's our frequencies. And again, we're assuming that A's ASCII value converts to 0, B is a 1, C is a 2, okay? So in reality, if we were doing this in real life, I'd have 127 here for all the possible ASCII values I would ever encounter, right? And really, there's more than that. There's 256, but really only 127 that we use. So our counting array would be bigger, so we've just simplified things. So let's just go with that simplification here, and let's animate that. So position 0, 1, 2, there's our ASCIIs. So I'm going to say for I equal n minus 1, starting from the A, right, position 15, right, that's the A, and I say, okay, what is the count for array of I? What is the count for the A? Well, the count for the A is a 3. 3 minus 1 is 2. So I'm going to put that in position number 2. So I filled in the last A of all 3 A's. Then I move backwards. But I got to decrement the count from next time I run into an A. So now I go to the F. So I'm not doing this in any order, but I got to figure out where does the last F go? Well, it goes in position 16 minus 1. That's 15. Decrement the count. Now we got position 15. We only had one F, but remember we added those offsets, right? So we're done with our Fs now, right? Then we do our Cs, right? That goes in position 12 minus 1. Decrement the 12, and off we go. So we're just jumping around, figuring out where to put the next letter in our output array and slowly decrementing our counts until we get all the way back down to position 0, right? So while I is greater than or equal to 0, and we're done. And so it fills in that thing in linear time, which is pretty darn cool, okay? So we got 2 passes. We've got the accumulation pass and then the offset pass. Well, we got the accumulation pass, then we have the offset pass for R, and then we have the output pass, okay? So, and it's not going to really change. It's a tightly bound algorithm. The worst case and best case scenarios are the same, but we get a linear cost pretty much. And our auxiliary space is 2n, right? We need twice as much memory as usual. And usually it's true that if you take more memory, you get more speed. It's kind of somewhat intuitive, I suppose, right? So we would say this is linear on the scale of 2n plus r because it cost us r in the loop, right? So if I go back one more time, so that r loop, beep, sorry, get back up there. This is our R loop. Add the counts, 3, 8, 12, etc. That's our R right there. Okay. So that's really all we got to pay for that thing. Okay. So and we look at that and we say, okay, well, it's of order, and we'll talk about this notation big O. You've probably heard people say big O. Big O means worst case. It's a shorthand for, hey, what's the worst that's ever going to happen? Well, it's going to be n plus r. So people wave their hands and go, oh, that's big O n plus r. What does that mean? It means the worst case scenario, it's going to be n plus r for our calculations. Okay. In this case, that's gonna be the array copies. Okay, and that's our counting sort. Okay, counting sort. So next week, we'll move back to recursion, divide and conquer with two very well-known sorting algorithms, merge sort, which is a bottom-up algorithm using recursion that will blow everybody's minds, and then a quick sort top-down other sorting algorithm. Both of these are n log n. So these are kind of the gold standard, although there is a faster one now, a hybrid called timsort, which is very well known now and is used in Python. So we'll make some references to that, but we're really going to study these, and that will get us through the end of next week. Okay. Thank you, everybody. I'll stick around. Otherwise, I'll see you on Tuesday. Have a great weekend. Thank you very much.